everyone, and thank you very much for inviting me to this very interesting forum. Learn a lot. I think I'm the only person in agriculture in the room, but what I hear about digital twins is very encouraging and how we might apply this in agriculture. And my name is Juan Landivar. I work with colleagues from Purdue and now from NASA. Akash Ashapur now is in NASA, and Texas A&M Agri-Life Research and Extension. And I see one person from Texas A&M Corpus Christi, Texas A&M University Corpus Christi. Well, digital twins, most of the day we hear about digital twins uses in engineering, structures, cities, and so on. As a digital replica of physical devices. For us in agriculture, this is the equivalent of our cities. This happens to be a field in 1921 and 2021, developing, see from about a month after planting and see how he develops to 420. And let me set up my alarm, my stopwatch. And then eventually develops, and finally, at the end of the season, we would like to see this beautiful field full of cotton. So the performance of that field and the development of the crop is key, to obtain a product like this at the end of the field. So these are our cities, so you can see the similarities, between the presentations that we hear early, and the presentation that I'm going to make. I borrow a couple concepts, a couple lines from the introduction of that Jan gave us. Digital twins is a virtual representation of real world entities synchronized to specify a frequency and reliability. I like that. The concept of digital twins can be traced back to numerical simulations, where theory and or data-driven methodologies were adapted to make predictions. That's exactly what we're doing. So Jan put it real well in his introduction. Say, now, how can we use digital twins in agriculture? Well, that the rapid development of sensing, communications, and computer technologies has accelerated the development of digital twins in other models, to simulate real-world conditions with real-time data, improve operations, and enable optimization of management alternatives. This also is a modified statement from Jan's introduction, but it has that real-world conditions, real-world timing, to improve operations and optimization of management alternatives, for our agriculture crops in this instance. And agriculture is not isolated from this explosion of technology to collect data. We are capable now of collecting massive amounts of data from every square meter of the field. This is an example at the experimental level, where we have a segment of a field, from emergence, and you can see the progression as the crop develops into a full canopy cover, and then beginning to senesce, and then produce a cotton crop. And then, we can collect data for every meter square of this field, and then, of course, that analyze the data and develop this type of functions. The wavy line that you see here is the data, and then we develop these models, for canopy cover, which is the green fraction within the meter square, expressed as a percentage. And then canopy height, is the surface of the meter. Canopy volume is a measure of biomass, and then a couple efficiency terms, on how green the canopy is. For example, this green is darker than this one, so this indicates that the plant is healthier. And the interactions of all of these functions, results in yields. So, in our view, a digital model, this is the physical thing, and these are digital twins for each one of these features: canopy cover, plant height, canopy volume, and so on. So this is our concept, just to begin with, that we can, with the time course of development of, measuring the time course of development of a crop, we can get to the, we can develop these digital twins. If we move to the field level, we can collect also massive amounts of data. For example, this is a field that is about 100 acres, or about 50 hectares, 45 hectares or so, and we have divided into grids of 10 by 10, or approximately 100 square meters or 1,000 square feet. So there's about 4,000 of these little squares here. And for each one of these squares, we are capable of measure and extract, the plant height, canopy cover, and all of these variables throughout the season. And this happens to be, this is one of our vegetated indexes, excess greenness. And this happens to be a graph that Jan made for us, where he extracted the 4,000 data points, and plotted here in this time course. This is a time, and this is the value. But there's 4,000 lines in here, and this is the kind of data that we use, that we got available now to develop our models. All right. What can we do within, or what are we doing within as far as developing the twin models? This is a field, the same field that I showed you earlier for 2019. You can see an estimation of the yield. For those of you who don't know cotton, this is a very good yield. Our average yields are about half of that, so this is an excellent yield, and it had to do with the pattern of rainfall that we had that year. And then we monitor the performance of the crop, from planting all the way up to harvest. You can see we divided in this heat map, into 5 groups. But the main thing that you need to, to pay attention here is that the red is low and the green is the high values. You can see the crop developing, and then eventually maturing. It will be very useful for the grower if he was at this point, to be able to have, to know what might happen here or how his crop will look out here. And that's what we pretend to do with the digital twins. Use previous data and some other data like probabilities of rainfall, in the future, to develop our twins. So this is one of our databases, 4,000 data points, and this is data for 2020, giving a little better yield, again, related to a better distribution of rainfall. But again, the same pattern of development, leading to maturity. Now, in this exercise, I'm going to use the 2019 and 2020 data to try to predict what happened in 2021. And this is what happened in 2021. That we have lots of rain, but not much at the beginning of the season, but lots of rain at the end of the season. Excellent yields again, and it's a slow start of the crop in this part of the field, but then it catch up. And then by the end of the season, we pretty much had 2 management zones. One, excellent, and then some waterlogged areas here along this low area of the field. But the idea here is, again, if we are at any point in this development of this crop, can we forecast what happened, during the following month, the following week, the following month, and so on, and what can we tell the grower, to do for management? All right, we developed this workflow chart, that just to I don't pretend you to understand what's happening out here, but just to give you an idea, we got these historical models that we developed from our previous data, and then with this very simple test, we compare, the real data up to any point in the season, with the historical models, and then decide, this is the model that we're going to use to forecast the future. And then we develop a combination of real data and predicted data. And that's what we use to develop our digital twins. And our digital twins are used to predict growth regulators, irrigation, crop maturity, defoliation, for the rest of the season. Or we can use those digital twins at any point in the season and then use it to get an early estimation of yield. If we get a new data point, we begin the process again, we come up with a new model, enhance our capabilities of predicting this data, and then enhance our capabilities of estimating yields, as you will see in a minute. So here is the exercise. We develop for 5 models, one for each management zone, for the red, the orange, the green, and the dark green, and so on. 5 management zones. This is the low yielding part of the field, all the way up to the high part of the field. So we got about 10 models. We could have 20, we could have 30, but we decided to limit it to about management zones per year, 2 years, 20 models. The same thing for these other variables. And for each one of our crop features, we have a set of these models. And these are our forecasting models. So then what we do is we use data up to any point in the season. Let's say that each box here represents a week. So for the first 4 weeks of the crop, we use real data. And then we select the best fitting model for this data here from the models that I showed you before for each one of these features that you see here in the title. And then, of course, as the season progresses, we replace real data for forecasted data. And then, of course, as the models become the predictions become more reliable, because we're using more real data, and so on, until, and we do this from emergence to defoliation. Every week, we add a new data point, and we try to come out with a new forecasting model. And here are some of the results. And again, I don't pretend you to follow everything, but the graph might be explicit enough for you to understand. We are here with four weeks of data represented by these green points. And then the gray points are the target. That's what we're trying to hit. And then the rest of the data, the rest of the red line and the blue dots come from a combination. We call it a hybrid model, which has a part real and part forecasted, resulting in this model here, which is the red line. And as you can see, we are here, and we are able to predict that point pretty closely. That point not so bad, but as early in the season, we get an error as we move too far away from the last point. But as more data comes in, you can see that the data fits better, the model. And then at the end, by the end of the season, of course, we are very much on top of it. So this allow us, for example, if we go back out here, to be able to forecast what water needs or defoliation needs, or excuse me, growth regulator needs might be, for this rest of the season. Okay, and here is an example of an actual recommendation that we give to the growers. This is a time sequence of the crop at maturity, beginning in July, and then toward the middle of July. And then with this function out here, we convert our efficiency term out here, excess greenness, to crop maturity, and then it results in this crop. And then based on this sequence of graph, we are able to give recommendations on the time and the amount of products that he might apply to the different colors of the map. For example, in this case, if the model would choose to apply defoliation in this date, he would apply to the green areas 7 ounces of this product, while to the rest of it might have been 6 or less. It happens that this field was defoliated on 7-10, and it was very close to the real thing. But that's the type of things that we're doing. For 2021, we began forecasting around this point, which was around 624, 630. the potential defoliation time, which this was pointed out here. And the model here is showing 719, if I'm not mistaken, and this field was defoliated at 724. So the model was not very far off, but as more data came in, the simulation got a little bit closer. Now, this is the most exciting part of what we're doing. We're using this partial twin models for every fixture, to try to predict yield. And this is the yield map coming out of the cotton pickers for the grower, and then we use that data to kind of assign it, to every 10 by 10 grid. And this is the resulting map. All right. And of course, the yield of this, was 1671. All right. And then every time that we get a data point, we use our digital twin models for canopy cover, for plant height, for canopy volume, for our vegetative indexes and so on, as input to a model, that forecasts yield. All right. So every week, we have new data that is fed into the model and to forecast yield. And as you will expect, the more real data that you have, the closer that we can get to the right yield. And this is what happened in 2021. With 1 month of data or 4 data points, we forecasted 1529 pounds. The real yield was 16 something, 1671 something. You can see as we replace forecasted data for real data, the model becomes more robust, and then eventually, it gets very close to the yield. In this case, over predicted, not much. It's very close, very much on the money. Is because we were not taking into account the whole field, but only the green areas. So we're very happy with the approach. We need to validate it. Of course, this is 1 year, but it shows, and this is we have done it with other data sets, that with approximately 2 months of data, we can begin to get reasonable numbers, to forecast the final year. We think that this is going to be very useful for marketing of the product. So our work last year, we concluded that yes, digital twin technology can forecast crop performance 15 to 30 days ahead. We could go more, I think, particularly at the end of the season, but safely I can recommend, that the next 15 to 30 days, you can have reliable data. And then, of course, that information could be used to estimate the need for growth regulator fertilizers and define defoliation timing, like I showed you earlier. Now, we're going to try to do the same thing that we did in 2021 for 2022. And this includes, further development, automation of the workflow process, and validation of the digital twin, against, the real yield data, and maybe begin to look at quality. And then, of course, we want to use those forecasts, to see if we can use it for marketing analysis. And then, something that we already began, of course, is, to incorporate Bayesian statistics, like the probability of weather event, to see if we can improve our forecasting capabilities. With that, this is our big dream, to develop. Right now, everything that I show you is drone data going straight into our models, for these tools, but in the future, the reason for the 10 by 10 grids is, that we would like to calibrate satellites and then use the satellite data, for the same thing, so we can cover large areas. With that, I thank you very much for inviting me to this meeting. I learned a lot from the previous experience. And Jan, I didn't want to pass the opportunity to display this. Sure. You are aware of this position that we have available at our center. It's for a data scientist to help us developing these digital twins. So if any in the audience has any student that might be interested, my information is there, or you can find time in the system. Jan, that's all that I have. Thank you very much for the invitation again.
Thank you for the talk. Do you have any questions from the audience? Okay, so you have Juan's contact information, and feel free to forward. If you need the link forward to you, and Juan, do you want to just pass the link of the position and other information to the chat room, so that
Yes,
others
sir.
can easily copy and paste to to their colleagues? Yeah,
yes,
that's great.
Yes, we are biologists, and I learn a lot on what you guys are doing with data analysis and so on, and I think that we need to find a way of linking with data scientists, to help us biologists making more progress in our work, and I think this person, could serve as the bridge between the two disciplines. Thank you very much.